Okay, I'm just going to do a little introduction here. My name is Tom Sherlock. I'm a user interface developer here at Wolfram Research. I work on the Mathematica front end. And again, I'm going to talk about some of my hobbies, in this case, astronomical image processing and astrophotography, and how I use Wolfram language to accomplish this. As always, if anyone wants to chat, you can send me a chat message or and ask questions during the presentation. Okay, so as I said, we're talking about how to do image processing using Python and Wolfram language. And Mathematica provides a very convenient and elegant interface for doing this. So as I said, Mathematica's powerful astronomical image processing capabilities can be further enhanced by taking advantage of the built-in Python interoperability. And by doing so, you can take advantage of resources that are available in Python that can enhance your astronomical image processing. So the question is, why use Python? Well, I've given talks like this before, not dealing with Python, but dealing with astrophotography. And the big problem you're trying to solve in astrophotography is getting good images with low noise. And the things you're photographing are, by their very nature, very dim, and there's a lot of noise from different sources. So you want to try to eliminate as much noise as possible. And the traditional way of doing that is taking a large number of images and adding them up. And before you can do that, they have to be accurately aligned. So instead of a blob of stars, you get one star. So, so this involves like aligning the images together. And you could do this manually, which is a real tedious process, or you can have your software do it for you. The Wolfram language has powerful image alignment routines built into it. However, they're not really specialized for star fields and dim objects. They're more geared towards photographs you would take outside during the daytime. So you really need a specialized routine for accurate astronomical alignment. There is such a routine, and I've included a reference to it down here. And the way it basically works is it divides up a field of point sources, and it divides it into triangular asterisms and uses those between images to compute the transforms, so the images can be accurately lined up. And this works very well. It's not a general routine, it's very specialized, but it works well, and it's available in Python. Now, I could have recoded the algorithm into the Wolfram language, and I was thinking of doing that for a while there, but this is also a good opportunity to show just how elegantly and easily you can use code from other languages, not just Python, but in this case, Python, to take canned algorithms which are out there and just drop them into your notebook and use them to do what you want to do. And also keeping parts of the pipeline, this image processing pipeline in separate processes, reduces the memory load in Mathematica. And with astronomical image processing, it's easy to load up a lot of stuff in Mathematica because the images tend to be very large and it just takes up a lot of resources. So it's good to keep them out of core as much as possible, and this solves that problem too. So first, a few prerequisites. Obviously, you have to have Python on your system. Luckily, Python is available for all the systems that we have Mathematica for. I'm using Python 3.9. That's available from python.org. So you have to install Python and also the Python package manager, pip3, on your system. And from the command line, it's very simple to install the modules that you need to do this work. There's pip3 install AstroAlign, that's the astro alignment routines, and pip3 install AstroPy, which is routines for reading and writing well, for doing a lot of stuff, but we're going to use it to read and write the FITS files, which contain the data that we're going to turn into images. And if you don't want to bail out to the command line, you can also do it from right inside Mathematica. You can find the external evaluators for the Python languages. We always use the first one to evaluate our Python cells. So take the first one, get the target, which is the actual executable Python name, and just run processes to install these guys. But that's just a bit of preliminary. Now let's go to the next thing and see what's going on. So this is how I took the pictures. This is my backyard, and this is my 120 millimeter achromatic refractor, which I use to take these pictures. It's a modest telescope. It's got a guide scope on top. This is the imaging camera. It's a monochrome CCD camera, and this is the guide camera here. And this is the computer where I captured the images. And right now, I've got this notebook in the same directory where I have all of the raw images. And I've uploaded a zip file with the same directory structure in it, so you can play around with this stuff yourself. But right now, I'm just setting this to be our notebook directory. So as I mentioned before, the camera I'm using is a monochrome camera, which is a typical CCD camera that takes a monochrome image. And this workflow will work for monochrome images. If you want to use it for color images, basically the calibration frames will all be done the same, but you would have to take additional pictures through colored filters and then combine them using color combine to get the different channels. And the filters can actually be red, green, blue filters, or you can have them be, for instance, narrowband filters, which pick out specific spectral lines like the oxygen 3 or hydrogen alpha lines, and have those be assigned to red, green, and blue. So you get a pseudo color image, but that would show you the chemistry of what you're looking at. We're not going to do that right now. That's kind of an exercise for the user. I invite you all to do that. But maybe next year I can show you some of the narrowband imaging I'm planning. So as I said before, the goal with astrophotography is to get as much signal and as little noise as possible. And the way you have to do this is you have to, in addition to taking the picture frames, the image frames of the object you're taking a picture of, you have to take additional frames which capture and estimate the amount of noise from different sources. And so we're going to talk a little bit how we do that. I've talked about this in previous talks, and this is, there's no exception here. You still got to do this stuff. But this makes it very easy and clean to do it in this manner. So we're just going to go through that. Now, this noise I'm talking about, there's several different types of noise. And the main one is what I call thermal noise. So the CCD camera has the CCD chip. There's electronics associated with that, and it operates at a certain temperature, and the heat emitting electronics cause a false signal on the chip. So the way this is typically dealt with is by refrigerating the chip, and good CCD cameras have a refrigerator built into them, thermoelectric cooler, and they're regulated so you can specify, I want it to be at a certain temperature, and the chip will be cooled down to that temperature. And this is important because since the noise is related to the temperature of the chip, you could, for instance, build a library of these dark frames at a given temperature. And there's another type of noise called bias or read noise, which is an uncertainty in reading the number of electrons out of each CCD cell. And this is the way you estimate this is by taking a very short dark frame image. And when I say dark frames, I mean the camera is covered. So you're not capturing any light, you're just capturing this noise. So we take extremely short frames, which just capture this read noise, and they don't have any thermal noise associated with them. And finally, there's something called optical noise, which is a bunch of different things. Like, for instance, it might be caused by uneven illumination of the CCD chip because of your optical system. This is usually more of a problem with the bigger CCD chips where there's noticeable light fall off. In my case, the chip is fairly small, so it's not a big thing. But still, you have problems of like dust and garbage on your filters and in your optical system, which can cause shadows, and you have to be able to subtract that out. So we're going to take care of all of these different sources. So let's talk about the bias noise. So the idea is we want to take a bunch of these very short bias frames, and we want to average them together to create like a master bias frame. So right now I've got these stored in the bias subdirectory of our main picture location directory. So I'm going to set, you'll see why I'm doing this in just a second. And this is the output bias file name, which I'm calling master bias.fit. And this cell contains Wolfram language code, but you can see this cell here is a little different. This has got Python code built into it. You can see that because of the little Python icon. So I'm going to do this for the different types of calibration frames. But for this first one, I'm going to kind of go through it in a fair bit of detail. So these first 4 lines here, I'm importing different Python tools to handle the stuff we need. For instance, here from astropy.io, I'm importing the module which reads and writes the FITS files. These are operating system related utilities, and this is numeric processing utilities. So the first thing I do, notice here I set a Mathematica variable, which is just a list of the file names containing the bias frames. So we can pass that right into the Python code with this type of expression. So it's now just a Python array, and then going through the Python array up to the length of this array of file names. For each one, I'm reading in each one of the bias fits files. I'm pulling out the data in this line, and I'm concatenating this image data onto the image array. So I'm creating an array, a Python array, and each element in the array is the data from one of the bias files. And then I'm closing the fits file. So basically I create an array of these images. Now I'm just averaging them. The final image is just started out with 0 and in the same size as the first of the bias frames. And then I just add them all up, and then I divide them by the length of the array, and that gives me the average bias image. And then I write that out using these fits routines. So I can just do that right now, and it did it that quick. It read them all in, it averaged them, and then it spit it back out into masterbias.fit. Okay, so let's keep going here and see what the next one does. We got to do the same thing with the dark frame. And this is, as I said, we're estimating the thermal noise. So we're doing the same thing, setting up the file names here. And same exact sort of thing. The only difference in this case is for each of the dark frames, we're subtracting out the bias noise, which is going to be there even though you're reading in the dark frame. It's still going to have that bias noise in there. So data bias came from our master bias file. So we computed that, we stored it in a FITS file, and we subtracted it from each one of the dark frame images. So we're doing the same thing again. We have our list of dark images. We average them together, and then we write out the master dark frame right here. And it did it that fast. So we now have master dark fit. Sounds pretty metal there, but that's our master dark frame. Now, as I said, we have to do these flat frames. Flat frames are done a little bit differently. There's actually several different ways to do them. You don't actually even have to be outside to do them, although you can capture them by pointing the telescope at the evening sky before it gets really dark. In my case, I didn't have a good evening sky, so I just did it in my basement by pointing the telescope at an evenly illuminated laptop screen. You notice the white t-shirt, another essential piece of astronomical equipment here, which can also be used to further diffuse the light coming in. And this will give us an idea what the light fall off is on the chip. So it's the same scope. It's got to be the same scope because it's got to have the same sort of optical system. And so we're doing the same thing with the flat files. I have an additional routine here to help normalize the flat files. The one trick with the flat files is you don't want to, you've got to play with the exposure so you don't saturate the images. Otherwise, you won't get useful data. And so you have to play with maybe do histograms so that the image histogram comes up right in the middle of the exposure range. And I actually wrote a routine to do that. But that's not going to be part of this talk. That's still experimental. So for each one of the flat files, again, we have to subtract out some of the noise. Here we're subtracting out the dark frame noise, or we're loading in the dark frame noise. We're loading in the bias frame noise. And then for each flat frame, we subtract out the bias noise, subtract out the dark noise. We normalize the frame, and then we add it to our collection of flat frames. And then we average the final flat frame in these lines right here. And then we write that out to our master flat frame file. And there I did right there. So I read these two in. It subtracted that data from each one of the flat frames, averaged them out, and wrote it out into master flat. Okay, so this is where it gets kind of interesting. This is where we're actually doing the alignment and stacking of the image frames. Everything up to this point was just kind of the preparation for this stage. So, so as I said before, by averaging many images, we're going to increase the signal to noise ratio of the final image. And before we can average them, they have to be precisely aligned. And the reason why they may not be in perfect alignment is because of mechanical and atmospheric noise captured during each subframe's exposure. Your mount may not be pointed exactly at the polar axis. The stars might be drifting. There might be little imperfections in the gearing system. Your tracking scope may be having problems. So so that's why the images don't come out exactly pixel for pixel alignable. They have to be aligned with this process. So for this example, we're going to use an image of M13, Great Globular Cluster in Hercules, which is the largest globular cluster easily visible from the northern hemisphere. So we can actually see what this looks like because we have images of these things in our astronomical image database. So this is our M13 image. But we're going to see if we can get close to this good image right here. So I have these all in a subdirectory called M13. Yes, I'm doing the same thing here. I'm loading in, creating the list of files. And then we're doing the same thing, except in this case, we're also importing the astro alignment module. So again, we're loading in the master dark frame, loading in the master bias frame. We're taking the target for the alignment to be the first of the light frames. It doesn't have to be the first one. We're just doing that. You can easily change the routine so it uses any particular alignment frame, but this one we're going to take the first. And we're calibrating the target frame by subtracting out the dark noise and the bias noise. And this is a bit of fiddle-dee-dee here because the data coming from the FITS files is in big endian format, and the alignment routines work with low endian format data, so we have to swap it around. So we have our list of aligned frames, and then for each frame in our light files, we open up the file, we read in the image data, we close it, we subtract out the dark noise, we subtract out the bias noise, we swap around the bytes so we can use the alignment routines, and then we call this. This is the registration routine, which aligns our image data with the target data. This is the main routine right here. And then it takes the aligned frame and it adds it to our collection of aligned images. If it fails, and there are a lot of reasons why it could fail, for instance, there could be clouds in the image, and you might have bumped the telescope, it will say, you can't align that one, and we're going to skip it. And it won't be able to align it if you can't find a certain number of stars. So, and then again, we're just going to take a thing and we're going to add them up and average them out and write it out. So let's just do that and see how long it takes. So right in the dark frame, we're in the bias frame. It found 30 images. And this is the target frame, it's the first one. It aligned them, it stacked them, and it wrote out the final M13 file. So that went pretty quick. And it just shows you the benefit of using a highly specialized algorithm in this case. So now we have to fold in the flat field. And for this step, I'm going to use a routine built into Mathematica, one of our good image processing routines, called brightness equalize. So I'm going to load in the flat frame. Load in our M13 frame. And now I'm going to call brightness equalize. And there is M13 with the flat frame, but it's still kind of muddy. So we're going to do some additional work on this. And this is what the image histogram looks like. And it's pretty typical. Most of the data is down here in the very low end of the range. And that's typical for astronomical images like this. So now what most people do is they take the result and they bring it into Photoshop, and then they play with the Photoshop curve and levels tools. Now I don't have Photoshop, so I'm just going to do that right in Mathematica. And the idea with the curves tool is it's just a really, really fancy way to let you drag around a curve to create the function which takes the input image into a stretched output image. And the one that works best for me is a curve kind of like this, kind of a segment of a circle. And this is just an approximation. I could have gone to a lot more trouble to get something like this, but it seems to make this more adjustable. But this works pretty good for me, and this just shows you how easily you can whip up something like this in Mathematica. The other thing I use in Photoshop is called the levels tool, and I always use it in the same way. I basically find the lower end of the central peak of the of the peak of levels in the image histogram, and then I stretch from that point on into the interval 0 to 1. And we can do that in Mathematica very easily too. I just wrote this routine called level image. And so what this does, I'm just going to, image levels is like image histogram, except it gives you the actual values out. So I'm selecting all the image levels that are greater than this threshold I'm passing in, and I'm taking the first one of those. They're actually the X value of the first one of those. So that's the left-hand side of the peak. And then I'm using our own stretch routine to stretch that into 0 to 1. So by combining the level image and the curve image routines, I can basically duplicate my Photoshop image processing cycle. So let me see what happens when, okay, so there, that brought out a lot more of the stars in M13. And now I'm going to do a mild deconvolution to sharpen the stars, which the fuzziness around each one of the stars is mainly due, I believe, to the chromatic aberration in the achromatic refractor I'm using. I've filtered out most of that by using the pale yellow filter, but still there's a little bit left, and that's what we're seeing here. So that can be removed by just doing a mild deconvolution of a Gaussian point spread function. And that, you can see, sharpens up the stars a lot without introducing artifacts. And then I can finally do a final stretch on that to darken the background. And that's our final image. And I'm going to export that. And that's, and using, in this case, I'm just using Mathematica to export the image straight away. So I did another example here too, which is a little dimmer object. And this is using the same dark bias and flat frames, but with different image frames. In this case, it's the group of galaxies around NGC 7331. And so this is what our canned image looks like of that. And so I'm going to process the files and using the same exact routine. So it's bringing the master dark, master bias. There's only 6 images in this image stack, so it went by a little quicker. And so that's NGC 7333 plus other galaxies. And if I do the flat adjustment, and then I do brightness equalize, you can see it doesn't look very exciting right now, but you can see a little faint fuzzy there. And this is, it's not a central bright image, so the image histogram looks kind of all over the place. But if I do the curve and stretch, you can start seeing different galaxies come out here. And let's deconvolve that. And it's starting to look a little bit better. And we can do the final image stretch on it. And you can see the galaxies. If, for images like this, I would probably need to do a longer exposure. This was kind of, let's see what we can do before we take down the equipment type of exposure. And I finally fed this into an external program called All Sky Plate Solver, which identified the different stars and the different galaxies in the image. So you can see the full extent of NGC 7331, and the fact that we only captured the small core of the image right there, plus all these other little satellite galaxies. So that is about it for today's lecture. Mathematica can be successfully used in conjunction with Python to take advantage of many existing astronomical packages. And this is just one example. And this will work with Mathematica's already powerful image processing capabilities to get a good synergy and workflow opportunities there. So I have to ask, do we have any questions? We're about at the end of the time, but we still have 10 more minutes of question time. So I'd be glad to answer any questions. As I said, I've uploaded the file, which contains all these subframes and also all the code that I use to process them. And we can, and you can play with this yourself. And let's see, Thomas Branham said, any suggestions for adapting for use for hydrogen alpha solar use? A pressure-tuned Lunt hydrogen alpha solar filter. Well, with a with solar astrophotography, it's kind of a different game because you have plenty of light in that situation. So we really don't come across the problems that we would that come up with all these calibration frames. But you can still use this to take a bunch of pictures and stack them up in the same exact manner as I did with the image alignment part of the workflow. So yes, you can do that using a hydrogen alpha solar filter. Let's see. So Arbin says, thanks, Tom. I hadn't considered how our Python hookends could be used in this context. That definitely opens up options a little bit. Yes, I was quite surprised at just how well this worked when I tried it out. We have a very good feature here, the ability to throw like Python code or other language code into cells and make use of Mathematica's interoperability to do things like this that maybe you don't want to do in a Wolfram language. And this is really a good example of just how powerful that feature is. And let's see, Dennis asked, how do you download? Well, I'm not sure there. You'll have to refer you to the system administrator. Lincoln, thank you, Tom. Best practical example of Python integration I personally have seen to date. Oh, that's good. Good. We'll play around with it, and I think you will find it's a very powerful tool. Oh, yes. Click the Files tab above the chat, and the file should be there. It's about 135 megabytes zip file. That includes this notebook that we looked at, plus all of the subframes that I captured for the M13 example and the NGC 7333 example. Nick, thanks, Tom. Are there any Wolfram language features that would make integration with Python even more seamless? Well, I'm kind of a newbie at it myself. I'm sure there are. And I had thought initially about just writing, chunks of Python external to Mathematica and just calling them as external features. And there's probably a lot of ways to do that. And with library link and math link. But I think this particular application where the Python code is right there in the notebook is the best because I could play with that. I could make changes and modify things right there. And it brings all the power of our interactive notebook environment to using these other languages. So I think, unless you have something very highly canned and developed, I think I would try to keep everything in the notebook, frankly. Yeah, that's right. Dark field noise probably isn't going to be an issue with solar, and probably also the bias noise. But I think you can certainly use this to stack all sorts of images. Now, one issue with the solar thing is, it's not really an issue, is the sun's chromosphere is going to be changing, but you're not going to need extremely long exposures with the sun either. So I think this will work pretty good. Also, I should say this is probably superfluous, but there's two different types of hydrogen alpha filters. There's the solar hydrogen alpha filters, and then there's the dim object hydrogen alpha filters. You cannot interchange those two. Solar hydrogen alpha filters have a large energy rejection filter on them, and you cannot use the dim object ones that I was talking about earlier to look at the sun. You'll just, it's far too dangerous. So don't even think of doing that. The solar filters are extremely specialized and quite expensive because they've got energy rejection components. They've got a Fabry-Pro Eidolon in there to tune the things. So I would like to have one of those, but I also have other things to spend money on. So I think we have, is there a database of photos we can draw from to experiment in Wolfram language? There are databases of photos and that people sometimes make available. So most people like to just put their finished photos on the internet. But occasionally you can find places where they'll put the raw subframes on the internet so you can play with them. And I found a couple of these places over the years. I'm not sure if they're still up. A good resource is this website called astrobin.com, which is a website devoted to astronomical photographs and astrophotography. And also the Cloudy Nights website is also a good resource. So I would start in those places. Let's see. What do you do to get the multiple languages drop-down menu on the left side of the notebook? I'm not sure how to answer that question.
Hey, Tom, just a quick heads up. You only got about a minute left.
Oh, okay. Yes, we have about a minute or two left before we get cut off. Any final questions that I can answer quickly? If not, you can send me a message through the conference website, and I can answer that as quickly as I can. Or you can just send it to me by way of Wolfram Research, and I will try to get that answered as quickly as I can as well. Okay, I think we're about done then. So I enjoyed talking about this, everyone. I hope you found it entertaining and not too frenzied, as is often the case with my talks. But I encourage everyone to go out under the night sky and get some pictures yourself. Okay, see you later. Bye-bye.